will start with the last session. Well, I will explain a little bit what I write. I recall that we are working with an algebra with a triangular decomposition, which is a triple of subalgebras, which satisfies certain condition about the gradient. Okay, Cornelia, I will try. You ask me when you want. I will try to explain the most possible that I can. So the first thing that okay, this is maybe the most important definition that I gave yesterday. That is the definition of an standard filtration. We will say that the module in the admits a standard filtration if there is a filtration of submodules like this, such that every subquotient, you quotient one by the following, you obtain a standard module for some simple T module. And maybe I will write the precise definition of this one, because it's not the proper standard module. This is without bar. It's not the same that we are working before. So in order that Cornelia understood a little bit more. So this, I recall this is defined as the proper standard module of the projective cover of lambda y I. This is the definition, and this PT, I will write PT, and this one, this is the projective cover, of lambda in the category of T modules. This is a new module that we introduced yesterday. And this is the definition of standard filtration. And this is important because what we will prove today, and it's most or less this lemma that I write there, is that the standard modules, this module, allow us to construct the projective modules in the category of module over A. Okay, so if you have a question, let me know, Cornelia. And we end the class, the last lesson, with this lemma. We proved the first part, and we will today to prove the other three parts. So the first part of the lemma says that this standard model that I just defined is a projective cover of inflation in the category of B minus modules, When we see this just to B minus model, it is the projective cover of inflation of lambda. And we will prove, and the other point say that the X group between the standard and proper standard are the Thiel and 0. And this proper standard model was introduced yesterday, and you can think on this as dual to. You can think this as dual of it is not exactly this, but you can think of this for the moment. It's enough just to understand or to have a picture of what these points said, because we didn't use it. And what is more important is these other 2 points, which say that if you have a module which admits a standard filtration, this means that M is here. This is this was the note, this definition. If a module admits a standard filtration, then it is a projective in the category of V- modules. And this is a quite nice property. And also this other part, the last point, say that if you have a graded module, which is projective as B- module, then it admits a standard filtration. This is more or less like a if and only if, but not exactly, but they give you us a very good characterization of the module admitting a standard filtration. And then we will use this to prove that every projective module over A will be admit a standard filtration. So this is so yesterday we proved the point 1, which is each. Okay, let me say something about the proof. A and B. I don't prove now B, but these 2 points follows using the Frobenius reciprocity. Which is, to prove this, we have to use a trick similar the trick that uses to prove that the head of the proper standard module is simple, where we use this Frobenius reciprocity. The proofs are similar, and I didn't prove it now. You can see the proof in the papers, but I would like to prove these 2 points. These 2 points. So we will prove this now. Let's see. Okay, C and B follows using followed by induction. We will prove the case so let me say more precisely. Followed by induction in the large of the standard filtration. We will prove we only prove the large of the standard filtration, because you see here we have the standard filtration of large S. We will prove it this followed by an inductive argument, and we will prove the case where S is 2. In order to see this is enough to see how this works, and it's a nice proof. We will prove the case S equal 2. So we will assume that we have a filtration M, which is M0, contain M1, and contain M2 equals 0, such that M0 quotient by M1 is isomorphic to a standard module for lambda, and M1 quotient F2 is isomorphic to lambda mu for some lambda mu in simplest T models. So we will prove this case, and the inductive argument use the same method that we will use in a minute. So so M is has a standard filtration of this way, of this form. So notice that so we will note something now. As you say, in this case, as we are assuming this, and M2 is 0, this means that M1, this submodule, has to be isomorphic to lambda to mu to the standard model of mu. So this, say then, M1 is isomorphic to mu, to the standard model of mu. So and now if you see this, because of this, M quotient by delta mu is isomorphic to delta lambda. So in other words, what we have M fits an exact sequence okay. Decimal. Okay, the first more space. This one. We are assuming that M admits a standard filtration, and the definition of the standard filtration is that M has a submodule, a filtration, but submodule. That means that we have M equal to M0. This contains a submodule M1. Just because M2 is 0. As we are assuming M2 equals 0, then M1 has to be isomorphic to nabla, because we to delta, because it's the same to quotient by nothing. Just okay? Okay, perfect. So because of the reasoning, this means that we have M fits in an exact sequence like this. To have this isomorphism is the same that say we have an exact sequence of module in this way, in this form. Now we use that. I recall what we want to prove. We want to prove that M is projective as a. We want to prove. I will write. We want to prove we want to prove that M is projective as B- modules. Okay, so we can see this exact sequence just as an exact sequence of b minus modules, as a module over b minus, and in this case, this delta lambda is projective. This is the first part of the lemma. The first part of the lemma, this is projective. And if it is as delta is projective, there exists a section of this map S. So I will call this S. X. This map exists because delta lambda is projective. Exists because delta lambda is projective. Is projective in the category of b minus modules. So let me call this P, and this section satisfy that oh, where is the proof? P composing with the S is the identity. Okay. And to have a section of this projection in an exact sequence implies that M is isomorphic to delta mu plus direct sum delta lambda in the category of b minus modules. This is because there exists this section of the projection in an exact sequence. You can, if you are not familiar with this, you can see the book of Curtis and Reiner, and this is a common argument in group and in representation theory. If you have an exact sequence with a projection and a section, then the term in the middle decomposes in the direct sum of the object in both sides. Okay, and now we are, because this is projective and this is projective in the category of B minus modules, and the direct sum of projective module is again projective. Because the direct sum of projective is projective. And then this completes the proof of the part C. Are there some questions? Not? Okay. We will prove now the last part of the lemma. I will erase this to Okay. Yeah, fine. And we will prove now the part D. We are here, sorry. We want to prove now that if a module is greater than a module, which is projective as B minus module, then it admits a standard filtration, like this here. So we will prove. The proof is also by induction in the length. Okay. It's also by induction. Induction in what? I will say now. Okay. Here, yeah. Okay. As M is projective in the category of graded model over B, then M is isomorphic to a direct sum of standard models for some and this is called because as the standard model are the projective cover of the simples, every projective model decomposes as the direct sum of projective module of projective covers. So we have this. This is the first thing that we can say, and the proof of this part of the lemma will be by induction on the how many direct sum we have here. The proof of M admits an standard filtration follows by induction on S. Yes, this S is this S of here. And as before, we will prove only the case in which S is true, because this gives you an idea of how the induction follows, how the inductive argument works. So we will assume that S is equal to 2. So we can assume in this case, we can assume the following. That M is isomorphic to a direct sum of the following form. mu in the category of T minus modules, such that here is the we are all in the graded setting, so such that the degree of mu, we will assume that the degree of mu is smaller than the degree of no, the other way around. I want degree of lambda lower of the degree of mu. Okay, we assume this, and then we will analyze the submodule of M generated by mu and by lambda. Let M M1, I will denote M1, the submodule, the A submodule of M generated by mu. And you can imagine we will prove that this M1 will satisfy the properties of the M1 around the proof of the previous system. So what is M1? So in other words, it is equal to A acting on mu. We have to act by all the elements of A in acting by mu. And because of the triangular decomposition, we can decompose A in the following way. A is A minus multiplied by B plus acting on mu, and as I said, it is the same that to act A minus acting on B plus acting on mu. So we will analyze this part. We will consider the homogeneous component of this object, of this part. Analyze the homogeneous component of B plus acting on mu. So in this case, how is the homogeneous component of this? This is equal to, this is in which degree, sorry. How is that? It is equal to B plus, sorry, it's more easy to explain in the other. So B plus is all in degree, in positive degree. So we have B plus, the homogeneous component of degree I of this acting on mu, which is in degree, the degree, let me say that the degree of mu is D. Then this is contained, the degree, this is of degree, I will write the same, the degree of B plus the homogeneous components of degree A acting on mu, this is equal to E plus D equal plus D. Then B plus the homogeneous component of Y of degree I acting on mu, because we are in graded model, is contained in the homogeneous component of degree E plus D of the original model M. And now we will analyze the homogeneous component of degree E plus D. And here another point is that I is bigger than 0 because it's B plus is equal or is 0 or bigger. So on the other hand, we can see that the homogeneous component of degree J of M is equal to the homogeneous component of this direct sum and this is equal to the homogeneous, sorry, this M is delta. I don't know why. I put this is delta. Sorry, here is delta. So this is the homogeneous component of delta plus and we know that the homogeneous component of the standard modules are contained of degree D. Okay, this is 0. This is 0. Is different of 0 if J is smaller or equal to the degree of lambda. And this is also different from 0. So this is different from 0 if only if J is smaller or equal to the degree of mu. So in other words, the homogeneous component of the module M is different from 0 only if J is smaller than the degree of mu, because we are assuming that the degree of lambda is smaller than the degree of mu. So we have to put these two things together. We have that the homogeneous component of M is different from 0 only if the J is smaller than the degree of mu. And in the other hand, we have that when we act by B plus to mu, we obtain things which are in degree bigger than the degree of mu, which is D. So this will be 0 as B plus Y acting on mu is of degree E plus degree of mu, B plus the homogeneous component of degree I acting on mu is 0 if I is strictly lower than 0. Could you follow me, or I make a mess? I was too embarrassed. Let me know if you have a question. Bigger than 0. Yes, bigger than 0, because it's positive. Perfect. Thanks. So as you see, in this part, we just are playing with the degrees, and here we are using lemma 39. Here in this part, I am using lemma 39. Okay, so I will erase this part. So this means that now let me write, this is b plus 0, and there is some the other things acting in mu, and we have proved that when we act this part b the positive degrees acting on m, we obtain 0. So this don't give nothing. So as a sum module, this is a minus acting in b0, and b0 plus is t. So we can write t acting all of this in mu. And this is the submodule generated. This is the same that b minus acting on mu. So this is the submodule generated by mu as b minus modules. So it has to be delta mu. So we have proved that the submodule, the A submodule generated by mu is isomorphic or equal to the standard module m mu. So this gives the first part of the standard filtration that we are looking for. Then m equal to m0, m1 equal to the submodule generated by mu, and m2 equals 0 is a standard filtration of m. And I will be a little bit more precise. In fact, m1 is isomorphic. m1, which is the same that m1 quotient by m2, because m2 is 0, is isomorphic to delta mu. That is what we proved. And m0 quotient by m1, which is equal to m quotient by m delta mu. This is isomorphic to what? As you say, we have that m is a direct sum of the delta mu, which is the submodel generated by mu, direct sum delta lambda. So when we quotient out, we want to take this quotient, I will write it here. This is isomorphic to delta lambda. And this proves that this is a standard filtration of M. In this case. The main point here is what I try to explain here, applying with the degree of M. And this completes the proof of the lemma. No, we are finished at least in the case when S is 2 and the part of the induction is left to as an exercise if you want. Sorry, I don't know if somebody has a question. We will start the last part of this course. Okay, I will ask all of this. And I will write a corollary of this that I actually write yesterday, and the corollary for 4 of the PT, which say that all projective modules in the category of A modules admit a standard filtration. And that means that you can construct projective modules over a triangle, over an algebra with triangular decomposition using these standard models, and that is at least is a very good reason to study standard models. And the proof for graded modules, that means in the case that you have C equal to G, the category of graded module, this follows from the last point of the lemma. Follow from 4T since if M is projective as a module, it is also projective as B minus model. So in this case, you can apply the last point. The last point say that if you have a graded module which is projected as B minus module, then admit a standard filtration. And in particular, this applies to projective A module, because if you have a projected A module, then it is projective as B minus module. And for the case for the case in which we consider projective modules without grading, in fact, we can, by a result by Gordon and Green, this other paper that I sent you, we can see every project model as a graded model. It's a graded projective model. And then follows, and then we can use lemma for 3 again. So this is the proof of the corollary. There is nothing more to prove. And the thing is that we can construct the projective model using standard models. And okay, we now can ask about we will now to close to prove the Bauer reciprocity with related the numbers of composition factors of a module with the subquotient in a standard filtration. To be more precise, we have this now. We let M a module with a standard filtration. And okay, what is a standard filtration? I will write again with standard filtration. M and 0, and S minus 1, and S equal to 0. And we define, we ask out this number. We can consider the set of I such that the quotient before that, given a simple module over T, we consider this set. We will consider the set of integers such that the quotient is isomorphic to delta lambda. Yeah, we have this. We have the standard filtration, and we have this set. It is. We want to. These are the set of integers such that the subquotient is isomorphic to delta lambda for a given lambda. So you can ask a natural question is asking about which is the number of the cardinal of this set. Yeah, and we will prove that this is equal to, we will write here the dimension over the field of the space of morphism between M and the proper co-standard module of lambda. We will prove this, so I will state this as a lemma. I will write this. I will prove this as a lemma. And I said before, this proper co-standard module is like a dual object of the proper standard model. I think we don't need the precise definition, so don't worry, Cornel, if you was not here yesterday. But let's give you an idea that this number is the same that can be computed by computing the dimension of this space of morphisms, which is very nice. Okay, there are some questions. If not, I will erase here and prove it. And we will use in the proof the part B of the lemma above, which is about the X groups. Even we don't prove it, this part of the lemma, because it's quite technical, but it's very important and very powerful. Proof. Okay, the proof also follows. It's followed by induction. By induction on S. It's followed by induction on the length of the standard filtration. But as before, we will prove the case S equal to 2, because this is the K argument in the inductive argument. So we will prove only for S equal to. So what we have in this case, we have as above a short exact sequence. To have this standard filtration, it's the same that to have this short exact sequence. Delta mu 0 for some mu and nu simple T models. So that we have observed in the proof above, to have in the case that the standard filtration has only 2 terms, in this case it's the same to have this short exact sequence. And now we will use a technical proof, a technical property of the X functors, which say the following. We applying by applying the factor x n lambda to this short x sequence to this, we obtain a long x sequence. This is very important property of the x factor, is that if you have a short x sequence, applying this factor, you obtain a long x sequence that I will write now, which is the following. It is starting 0, then go to x0. I don't write the subscripts. Let me write this. Delta mu. No, delta mu. Here is lambda, sorry. Here is lambda x1 delta mu. And this x sequence follow in the same way. Is the x factors 0, 0, 0, 1, then we will 1, 1, 2, 1, 2, 2, 3 at the infinite. You see here we have the term of the x sequence. We have delta mu, m, and delta mu, which are the term here in the short x sequence, and it's twisted because the x factor in this way is contravariant. But now we can use the lemma for 3 that ensure that this term here is 0. This is x1 of size between a proper standard module and a delta and nabla bar, and this is 0. This is 0 by lemma. This is lemma 4.3b. This is the part that we didn't prove. And the other thing that we have to note is that x0 is the same that home in the home space. So this, which is in principle a long x sequence, is really it is a short x sequence. It's of the form 0. Instead of x0, we can put home. I don't write this because I have not space. Wow. I don't have a space. I will write the same, but well, the exact sequence continues down. It is home of delta mu nabla lambda 0. This is the short exact sequence that we have. You can see it. If not, you can ask me what I write it. I wrote. Okay, so we have this short exact sequence, and when we transform this, okay, we have a short exact sequence of, in principle, they are vector space. So this, when we look for the dimension, this say that the dimension of home between M and nabla lambda is equal to the dimension of the vector space index in the both sides. Is equal to the dimension of home of M. Now, delta mu nabla lambda plus dimension of home of delta nu nabla lambda. Okay, in conclusion, we obtained that the dimension of the home space between M and nabla mu and nabla lambda is equal to the sum of the dimension between delta mu and delta nu, which are the terms of the standard filtration. So if we make a case-by-case analysis, we will see that we will coincide with the number which are that we wanted. Therefore, the numbers of E such that Mi is isomorphic to delta lambda is equal to the dimension of this, of home between M and nabla lambda. For instance, if lambda is mu, this will be, if lambda and mu are different, one of these is 1 and the other is 0, and we will obtain the same if we consider a number of subquotient isomorphism. And this is the equality that we are looking for. Are you understand the idea? No, you can ask me. Maybe. Okay, what is the time? 20. So just a notation, what is the notation here? So you see, because of this lemma, this number here is not depend of the standard filtration. Maybe it could be another standard filtration of a model. The model could be have two standard filtration different, but what is equal for every standard filtration is this number. The number of composition of subquotient isomorphic to each lambda, to each delta lambda, will be equal for any standard filtration that we take. So we will denote this number in this way, m delta lambda. This is the notation for this, similar to the composition factor when you take simple models. So we can now to state the Brouwer reciprocity and prove it. I will go here. Then for 5, this is the Brouwer reciprocity. Let lambda a simple model over T, and the project and P lambda. The P lambda is the project cover of L lambda. Then the number of then the corollary that I proved before the lemma, after the lemma, was that every projective model admits a standard filtration. So we can consider this number, the number of composition factor of the projective lambda, which are isomorphic to delta mu. And what say the Brouwer reciprocity is that it is equal to the composition factor of nabla mu, which are isomorphic to the simple model L lambda. So the Brouwer reciprocity gives us a very nice symmetry between these all objects which are very important, the projective ones, the simple models, and the standard and co-standard model we are introduced during the course. And because of all the work we are done until now, so far, the proof is more or less is not difficult. Okay, so we will start by this part. You have that okay, in the next way I will recall that. Okay, I recall that this is the number of composition factors this is the number composition factors of nabla mu isomorphic to lambda, to L lambda. Yesterday I recalled what is that. I don't know. I can remember. I can recall that. Recall that. Do you know, Corneli, what is the composition factor? Yesterday I wrote this. Francisco, you are in here, but Corneli not. I don't know. In order to recall it. Yeah, I ask if you know that the definition. Yeah, Corneli, know what is that? And yesterday I explained what is the number of composition factors. Now, okay, oh yes. And it is known, and you can see from the book of Curtis and Reiner, that a way to compute this number is the following, similar to above, is to compute, here is Curtis and Reiner, for instance. See, it is the dimension of the Hopf of the space of morphism between the projective cover of L lambda to the model that you put there. That is a way to compute the composition factor. You take the projective cover and calculate the dimension of the Hopf between these two modules. And that is what we write before in the lemma. That is just, we proved that it is equal to the number of subquotient of the standard filtration of P lambda, which are isomorphic to nabla mu, to delta mu. This is by lemma. The above lemma. I don't remember. I didn't put number before lemma above. This is the lemma that proved just before. So, and that is all, because we already worked a lot before. So this is all the proof of this proposition. Call it Brouwer reciprocity. And there is another instance of this Brouwer, a particular case of this Brouwer reciprocity, which is called BGG reciprocity. What now? This is proposition 422. It's also Bellamy and Thiel. Assume that So in this case, we assume that T is semisimple. And we assume that there is certain isomorphism between B minus and certain dual of B plus. I didn't explain what this means, but it's the dual of B plus with certain gradient in such a way that it is an isomorphism in T, in the category of T model, and it's graded. So that is the same that to put here that the gradient are isomorphic. In the category of ungraded models. So if this happens, then the Brouwer reciprocity has this form, this particular form. We can take this one. Instead to take the nabla, we put here delta in order, yeah, for all lambda and mu. And just to recall that, in this case, delta lambda is isomorphic to, is the same that delta bar lambda, as T is semisimple. In this case, the delta and delta bar are equal because T is semisimple. This is just an observation. And okay, so in this case, the Brouwer reciprocity is more symmetry, because in the sense that we have standard and standard model in both sides instead of nabla. It is more nicer, for say something. And I will just an idea of the proof. Because it's just an idea because I didn't define very well this object, but it's just a dual in the category. And what happened is that in this case, under our assumption, the graded character that I introduced yesterday are equal in this case. If you you can see the precise definition of graded character in the the paper. I use this graded character, this notation in the paper which I send you. And okay, and because of this, you can use this. You can use this equality to show that. So in this case, here bar. So using graded character, which the graded character gives a measure of the composition factors. So you can change this the number of composition factor of nabla mu, which are isomorphic to L lambda, because of this equality, is equal to the number of composition factor of delta mu isomorphic to L lambda. So this equality implies this. And also here we can use this is related also with the exercise 6 of the that I sent you today. Today I send you a file, a new file with the exercise. With the only difference is there is this new exercise. So using this and the equality between the graded character, one can prove that the BGG reciprocity. I want to show that, and then BGG reciprocity. This this is called BGG reciprocity. Sorry. BGG reciprocity is a particular instance of BGG reciprocity, of Brouwer reciprocity. Okay, so with this, I end here is okay. I end the first part of the course. I mean, with this we have a panorama of all the most important features of this algebra with triangular decomposition. We started by classifying the simple modules, and then we give a way to construct the projective module using standard modules, which is that proved above. And finally, we obtain these reciprocities, which give you an idea of how all these objects, projectives, standard, co-standard, and simple modules are related, and there is a very strong connection between them. And also, just to that's all. So this is. I hope you you enjoyed this part, and yeah, what is the difference? It's there is a big difference because the Frobenius reciprocity is a relation between the functors induction and restriction. I will add this here. The Frobenius reciprocity say that I'm sorry. This is Frobenius reciprocity. So the Frobenius reciprocity is a relation between the functor induction and the functor restriction, and this calls for any algebra A and B and module over them, and there is no matter. It's not only for algebra with triangular decomposition. This whole in general. And here is the Brouwer reciprocity, which is a relation between the dimensions or the number of certain composition factors or subquotient of a standard filtration. Yeah, okay. I didn't know. Okay, one can write instead of this isomorphic, of course, one can write the dimension of this is the same as the dimension of this, but this holds for any m and n modules, and not it's not so. Instead, the Brouwer reciprocity holds only for, you see, related only projective, standard, co-standard, and simple modules. And it is not a direct consequence of that. Of this is your question. Or we have to work a lot to reach this equality, and it is only hold for algebra with triangular decomposition. Thank you. Yeah, I like this because this symmetry and also this also is very important, and it's a nice property between this functor. This reciprocity is a general name to call this kind of relation between two objects with certain symmetry. And there are another question. Are there another question? Okay, I just to finish the course, I would like to mention some example of Hopf algebra where we can apply this. Unfortunately, I don't have time to say more about these Hopf algebras. Just a way to construct it. Even I will don't define Hopf algebra because I need more time. So let me see. And I hope that this first part was interesting for you, and I hope that you are I don't know if learn something, and also more, I think that more that learn something, maybe you have more questions than before, but you have an idea where to look for and reply this question, and also an idea of what is important if you are interested in representation theory, what kind of tools and results are important to work in representation theory. So, and now let me say something about applications of algebras. Okay, no, I forget the shit. Okay, so let H a Hopf algebra. A Hopf algebra is an associative. I want only to say that a Hopf algebra is an associative algebra with an extra structure such that such that if M and N are H modules, then its tensor product is also an H modules. For instance, if G is a group, then the group algebra over the field is a Hopf algebra. And in this case, one can note that the tensor product of two modules is again a module via the diagonal action. Could you put here, please? Okay. So for instance, notice that if M and N are modules over the group algebra, then M tensor N is also a module over the group via the diagonal action. How is the diagonal action? If you take an element of the group acting in the tensor product of two elements of M and N, this is equal to act G in the first tensor and also G in the second tensor. So that a Hopf algebra are associative algebras with a similar property to this. In general, they are not a group algebra. There are more examples where the action is a little bit more complicated, but just to have an idea, this is enough. Okay. And there is another, okay, these are a Hopf algebra. And there is another important algebras which appear in Hopf algebra, which are Nichols algebras. Which are quotient of the certain quotient of the tensor algebra of a vector space. Okay. Or it's a graded algebra and satisfy another condition, but we need a lot of more time to explain what is there, but it's just an algebra, and with these two ingredients we can form a kind of semi-direct product of algebra. And also we can form the Drinfeld double of this. Which is a new Hopf algebra. In other words, it's a new example. You have a Hopf algebra, you can construct the Drinfeld double, which is a new Hopf algebra, which have another property as it is a quasi-triangular, for instance, which gives an extra structure in the category of model, which is very important for applications. And what happened is that remark. this algebra, as we call it, is an algebra with triangular decomposition. With triangular decomposition, where the negative part, yeah, this is A. Where the negative part is this, the Nichols algebra. The center, the T algebra, is the Drinfeld double of the algebra H. E plus is the Nichols algebra of a certain dual of V. Another okay. We can so in this case we can apply all the results for algebras with triangular decomposition to this example. So I have no time to unfortunately I don't have time to talk more about Hopf algebra. It's just an example, and that's all. This is the way to, just also is useful to see that there are a lot of examples of algebra with triangular decomposition. In particular, this is a way or a path in order to construct several examples, and also these examples are important because the category of module of these Drinfeld doubles are quasi-triangular categories, braided categories, which are very important for application to physics and another area of mathematics. And that's all of this course.